Let us look at crystal field theory for octahedral complexes. We know that a metal atom is approached by 6 ligands in the case of octahedral complexes. So the d orbitals of the metal atom are dxy, dyz, dxz, then dx square minus y square and dz square. They are degenerate d orbitals, that is, they are having the same energy. But when these ligands approach this metal atom, there is an increase in the average energy of the orbitals. What causes this increase in average energy? Here in this crystal field theory, we are taking the metal ligand interactions to be ionic in nature. Ionic means there are electrostatic forces involved. So when the ligand or the ligands having lone pairs are approaching these orbitals, these degenerate d orbitals, they lose their degeneracy and their average energy is increased. And this results in the splitting of the d orbitals into two sets. That is, the one having an increased energy and another set having a lower energy, not as high as the increased energy set. Now let us look at the reason why this is happening. We know that in an octahedral complex, the ligands are coming along the axis, approaching the metal atom along the axis, that is, along the x-axis, y-axis and z-axis. And if you remember the orientation of the d orbitals, we know that there are interaxial orbitals like the dxy, dyz and dxz orbitals. In those cases, the lobes are lying between the axes, they are interaxial. Whereas in dx square minus y square and dz square, they are axial orbitals. That is, they are lying along the axis. So when the ligand is approaching along the axis, there is an increase in energy. That is because there is electrostatic repulsion between the metal orbital ions, that is the metal orbital electrons which are present in the partially filled d orbitals and the electrons in the approaching ligands. So that increase in energy results in an increase in the average energy of the orbitals, and that in fact results in the splitting of the orbitals into two sets, that is EG set having higher energy and T2G set having a lower energy. So the axial orbitals end up being the EG set because they are lying along the axis, and the interaxial orbitals become the T2G level. That is because they are lying in between the axis. And the energy gap between the EG and T2G is called the crystal field splitting energy. Here it is represented as delta O representing octahedral complexes. So CFSE, that is the crystal field splitting energy, that is delta O. Now there is an increased energy in the case of EG. We believe that each orbital is having an increase of 3 by 5. Out of the 5 orbitals, 3 are having lower energy. So 3 by 5 is attributed to each orbital. That means into 2. That is 6 by 5 plus 6 by 5 in the case of the EG orbitals, and each of these are assigned a value of 2 by 5. That is, this much energy is lowered here. So into 3 of them. That means 6 by 5. That is minus. It is lower energy and this is higher energy. Now we know that the average energy of the d orbitals have to remain a constant. Now this is according to a principle called barycenter rule. It is called the It's a barycenter rule according to which the average energy of the d orbitals have to be constant. So this is 6 plus 6 by 5 and this is minus 6 by 5. Ultimately there is no difference. So it is remaining constant. Then we can see that this crystal field splitting energy, this depends upon the following factors. One is the charge on the central metal atom. Delta O depends one on the charge on the central metal atom, that is the number of electrons present in it. So that will increase the repulsion. When the ligands approach, that will increase the repulsion between the electrons. Then second one is the strength of the ligand. And the third part is the position of the metal in the periodic table. That is, if it is occupying a position, the lower position, if it is towards the bottom of the group, it will have a larger size and it will be having more diffuse d orbitals. The d orbitals will be having a more diffused state. So all these things decide the strength or the quantity or the amount of delta O, that is the crystal field splitting energy, that is dependent on the charge on the central metal atom, strength of the ligand and the position of the metal in the periodic table. So if we recap once again, the degenerate orbitals lose the 5 degenerate orbitals lose their degeneracy with the coming of the ligands. There is electrostatic forces of repulsion. That is because we consider it as an ionic bond. Then with an increased energy, the orbitals split into two sets, Eg having higher energy and T2g having lower energy. The interaxial orbitals become the T2g group, that is having the lower energy because they are between those orbitals are between the axes. They are the interaxial orbitals. Since it is an octahedral complex, the ligands approach along the axis. So the Eg group have the dx square minus y square and dez square orbitals, which are axial orbitals. They are the orbitals lying on the axis. Then we have the CFSE or crystal field splitting energy difference between Eg and T2g group, that is represented as delta O for octahedral complexes. Now Eg group is having a positive or higher energy, that is each orbital is assigned 3 by 5 delta O. So they will be having two orbitals, that becomes 6 by 5, and T2g are assigned a value of 2 by 5 of delta O. So that into 3 orbitals will give minus 6 by 5. So ultimately the average energy has to be constant. So that is according to the Barry center rule. So the crystal field splitting energy delta O depends on the charge on the metal atom, strength of the ligand, and position of the metal in the periodic table.